So next I want to talk about how points to analysis, like I just explained it to you using Spark, then actually aids call graph construction. Maybe to some of you that relationship is obvious, but I still want to make it clear nonetheless. So the whole reason for why we are doing this points to analysis is that if we know now that the points to result, so the points to set of some variable O, only contains these allocation sites here, like new C and new D, for instance, then we know that any call foo to that same variable has to go to C.foo or to D.foo, right? Assuming that C and D actually implement these methods. So basically the types of the allocation sites that you have in the points to set of a variable, they tell you directly all the possible objects that could be the potential call targets for any call on that variable. The good thing about Spark's iterative algorithm is that it can be very precise. It can also be tuned very effectively. So I showed you already some options that you can choose, right, to merge certain nodes and not others. It does also not necessarily require an initial call graph. So there's actually a way to create call graphs on the fly. I'll still be talking about this on the next slide. But nonetheless, it's still flow insensitive, right? So it disregards execution order, but that's the regular case for call graph analysis. It can nonetheless be quite expensive to compute. So if you use a regular Anderson-style pointer analysis, it can take several minutes for larger programs, even though Spark is already relatively efficiently implemented. And also the pointer assignment graphs, they tend to become quite large. So in particular, if you choose rather precise representations of fields and their assignments, for instance. Let me quickly talk about this point here. Why does it not necessarily require some initial call graph? In Spark, you have the option to actually create call graphs on the fly using an indirect recursion. So basically, it means that Spark will start at your program's entry point, and this entry point actually has to be a static method. So, for instance, it could be your static main method of your main class, and then whenever it finds a new allocation node in that main method, let's say initially, right? So, for instance, some new A, and it adds that to the points to set of a variable P. It then finds all the virtual invokes p.m and adds a call edge to a.m, right? Because it now knows that A can be a possible target type of P. And then whenever inspecting a new method M that now can be called because it has been added to this call site, it creates new pointer assignment graph edges for all the statements in M, and then incrementally updates all the points to sets. So you have a recursion between creating new call graph edges and updating points to sets. So for instance, let us take a look at this example here, where we are creating first some A object here, which is then calling foo, which will resolve to that particular method here, which is then overwriting this variable, actually the static variable A here, with a new B object, which then actually makes potentially this foo method reachable as well. Then here we will start looking at main, right? So actually Spark will first analyze this procedure here. Then it will be analyzing foo, because that now has become reachable, because we know that foo now may be called on this type A here, right? So we will now analyze a.foo, and by analyzing a.foo, we now know that A might also be assigned an object of type B. So this points2 set here is actually being extended, and b.foo therefore also becomes reachable. And next we will be looking at b.foo as well. And then the analysis terminates there actually. So in the end, we will have this as our final call graph, and we'll have this as our final points2 set. And so through this construction, you basically get a call graph that contains all the methods and all their calls that are reachable from your program's entry point, and also the correct related points2 sets for all the variables. So you can use Spark to refine a call graph created ahead of time, as in VTA, or you can just compute call graphs on the fly. One question, of course, is what is actually better? And there are results that show that if you do on-the-fly creation, that is at least as precise as ahead of time computation of call graphs. So actually, in almost all the cases, this on-the-fly mode should be the preferred one. Yeah, so I've shown you how Spark works in general, and you can use Spark in its default mode, so not setting any particular option. Then you will basically get this Anderson-style subset-based pointer analysis that I showed you. But you can also configure it to do an RTA. Then it will basically use types for allocation nodes. So they're basically merged by their type. You have a single variable node only, and one points2 set for all the variables, right? So that's why, that's because in RTA, we don't distinguish individual variables, right? We just care about what is being instantiated ever. And so here, basically, RTA is just propagating all these allocated types to a single node. And so it's sort of an abuse of this powerful framework, but it works, right? In VTA, we have types as allocation nodes as well. We have set it to field-based. We are simplifying SCCs, and we are not doing an on-the-fly computation opposed to Anderson-style analysis, which is doing that. And there's also a so-called Stensgaard-style analysis, which is equality-based, like I showed you earlier. And there's an efficient implementation based on the union find algorithm. But in Spark, it's actually implemented also using the type propagation graph. So that's basically an alternative implementation for that kind of algorithm. So just to recap, call graphs model a program's calling structure at compile time. And we want to have a call graph that is sound, so it's not missing any edges, but it's also precise, so it has maximally few spurious edges. And Spark can compute reasonably precise call graphs using different variants of one unifying algorithm, like I showed you. And it can actually compute call graphs and points2 sets together on the fly, right? And then this actually enhances precision if you do it that way. That was all I had on call graph construction and points2 analysis for this week. So next week we will then be talking about how you can leverage this to actually conduct so-called inter-procedural analysis, which gives us a whole different set of challenges again. So I promise you it's going to stay interesting. I'll see you then. Bye-bye.